Okay, here we are again. I hope you had a nice 3-day weekend. So we're going to start up again with our discussion about this time interest rate risk. The first chapter or first section was about bonds and bond pricing. And there's one topic that I saved for after we've started a discussion about VBA. And if you recall, at the very end of section 1, you'll see there's a discussion here called root finding techniques. We're going to save this for a little bit because we're going to use this technique to solve for yield to maturity for bonds. But I think it'll make more sense to go over this after we've started to talk about VBA. Okay, so we'll save this for a little bit longer, not too much longer. And instead, we'll skip on to section 2, which is our discussion about interest rate risk. Now, if you recall from our discussions in chapter or section 1, there's an inverse relationship between the price of a bond and interest rates. As interest rates rise in the economy, bond prices fall and vice versa. And that's because, if you recall from this bond pricing formula, the price of a bond is the present value of the future cash flows, meaning the coupons that we still have to collect and the face value, which will be repaid to us in maturity. So algebraically, just by looking at this equation, you can see that if R goes up, each of these ratios will go down, and then the sum will, of course, also go down. And so the bottom line is interest rates and bond prices always go in opposite directions. And if you recall, we also drew a curve that illustrates this, the so-called price yield curve, where we saw that, let's see, I guess I did that in the Excel spreadsheet, but let me just sketch a new one in here for you. Just very quickly, if we plot the price of a bond against its yield, not only is the relationship inverse, in other words, the slope of this curve is negative, but you'll notice it has a special type of curvature to it. And we'll discuss this in more detail later on, but what we're seeing here is that the first derivative, this curve or function, is negatively sloped or negative. The second derivative is positive. Okay, so we'll see how important that is and why that matters in a bit. But right now, what we're going to do is try to understand how sensitive a bond's price is to changes in interest rates. I mean, given that there's an inverse relationship, it turns out that not every bond is equally sensitive to interest rate changes. For example, you might find that one bond has this very flat price yield curve, and another bond may have a very steep price yield curve. And so we want to understand what determines the sensitivity of a bond's price to changes in interest rates, with the understanding that no matter what's happening, when prices interest rates go in opposite directions, but not always by the same amount. Okay, so in other words, what we're trying to do here is capture how sensitive a bond's price is to changes in interest rates. And that, of course, means how risky is that bond to the investor. Okay, so that's what section 2 is all about, interest rate risk. So now, by the way, I just want to remind you that with corporate bonds, at least, there's also a component called credit risk, where there's always a chance that you might not receive the cash flows that you were promised. If the corporation goes out of business, they go bankrupt, whatever happens, then the investors are not going to get their money back, or at least not all of it. That kind of risk, we're going to treat it separately from this. This part is common to all bonds in the economy, even treasuries, which are free of credit risk. This is a different type of risk. This is falls into the category of market risk, meaning that the price of our assets could be adversely affected by changes in market conditions. All right, so we want to make a separation here, a distinction between credit risk and market risk. And specifically here, we're looking at interest rate risk. Now, it turns out that there are numerical measures available to us that can help us take each bond and determine just how risky it is. So this way we can compare them side by side. And so this way, if you're, let's say, a portfolio manager and you're looking at all these different bonds you could potentially buy for your clients' portfolios, it's pretty important for you to understand what could happen if interest rates change. Now, of course, as a portfolio manager, you're on top of the economic news. You're paying close attention to what the Fed is doing. You're looking at economic conditions, or at least you have a staff of researchers who are doing this. And so in rising interest rate environment, you might make different bond choices than in a falling interest rate environment. So it's very important to understand how sensitive each bond is to changes in interest rates before you make any decisions. So there are two classic measures that we'll be looking at here. These have been around for quite a few years. In fact, the duration measure that you're seeing here was invented, or well, first thought of in the 30s, 1930s, that is. We'll see in a few minutes by a researcher named Frederick Macaulay, who published a book about duration. What he was specifically interested in was understanding specifically how much capital an investment company might have to set aside to protect against losses in their bond portfolios. And since then, the duration measure has been expanded on. There's many different kinds of durations, but these are the traditional definitions. These are the easiest to calculate, but they're also based on the most unrealistic assumptions, which is, of course, the way it usually works with financial models. If you want more realism, you have to put up with a lot more complexity. So now it turns out that there's really two versions of duration that we want to consider here. They're very similar to each other. The first one is called Macaulay duration, after the creator Frederick Macaulay. And then it turned out that Macaulay's approach was a great idea. It was really a path-breaking idea that he came up with, but for many applications, it wasn't completely appropriate, because he was interested in different things than we are right now. He was really more, he was an actuary with an insurance company, and what he was trying to study really only applied to what he was doing. And so the more general version is called modified duration. That's the one that we use, we see used in Wall Street today, because well, you'll see why it's more convenient than Macaulay duration, but luckily the two are very closely related to each other. So if you know one, it's easy to calculate the other. So we'll start out by defining Macaulay duration. Now, this formula looks like a nightmare, but if you look at it very carefully, you'll see that really all we're doing is taking the bond pricing formula from last chapter or last section, making some tweaks to it. Let me just see if I can sneak it in here. We can actually read it. Yeah, that's not too bad. Okay, just as a quick reminder, actually, maybe I could even slide it down here. So basically, what's changed here is that all of the coupons have been weighted by this variable T, which is the time until they're received. Okay, and then at the end, that N is also a time. Remember, we defined N to be the time at which we are repaid our principal or face value. So in other words, what we're doing is we're weighting each cash flow by the time it takes until we actually receive it. And then, of course, we add them up. And then when we're done, what we're actually doing here is dividing by the bond's price. Okay, or multiplying by 1 over the bond's price. And this is our Macaulay duration. Now, the beauty of this is that it's so easy to calculate it in Excel, but the interpretation of it is a little bit tricky. So that's why we usually instead use the modified duration. It's really all about the interpretation. So, for example, let's see how we could do this in Excel. Now, I've already got a spreadsheet set up for this. And what you're going to see here is, let's see, what are we? Oh, I guess what must have happened is I must have put this on sheet number 1. Okay. Well, I guess we'll get back to this. I've forgotten which example this is. We'll get back to that later on. This is sheet 1. Okay. Now, if you notice, it's set up in a nice little table. It's so easy, like I said. What do we know? It's a 4-year bond. Now, by the way, we're assuming annual coupons just to keep it simple. We'll see later on how to adjust it for semi-annual cash flows. 4 years, annual coupon of 70 right here. Now, by the way, the word CF here stands for cash flow. The reason why we're doing that is because there's two different kinds of cash flows that we could receive from a bond. One of them is the coupon payment, and the other is the repayment of principal or face value. So just to keep it general, we'll call this cash flow. So you can see in year 4, we're getting our coupon of 70 plus a repayment of the face value of $1,000. What else do we need to know? Face value is 1,000. Let's tell you what, let me put this over here. Just to summarize everything. Just so you can see exactly what's going on here. Well, that's strange. It's just basically disobeying me here. Okay. All right. Anyway, but the market price is 960. That's listed right here. Now, we did mention last time, one of our earlier meetings, that the only 2 days on which the bond's price is guaranteed to equal the face value are when it's first issued and when it is redeemed at maturity. In between, the price can fluctuate depending on market conditions, specifically what's happening to interest rates. So you can see this bond is selling for 960 when the face value is 1,000, and that means this is not a newly issued bond. It was issued at some point in the past, and it now has 4 more years until the maturity date. So it could, for example, have been a 30-year bond that was issued 26 years ago. Okay, so that's the only way the price can deviate from the face value. If this is a brand new issued 4-year bond, it would be selling for $1,000. Okay, so any other time, it could be, the price could be literally anything, depending on what's happened to interest rates since the bond was first issued. Also, the yield to maturity is 8.21%. That's listed up here. And that's a reflection of, as we mentioned before, the maturity of the bond, interest rates in the economy, and then the credit risk of this bond, of course. The riskier the bond, the higher will be the yield. Okay, so typically, let me just mention this here, the yield to maturity increases with credit risk. Okay, and the coupon rate. The higher the coupon rate, the higher will be the yield, because the what is causing that? It's really being very weird with me today. Let's try that again. The yield will increase as the credit risk increases. Okay. The higher the coupon rate, the higher will be the yield. Holding everything else constant, of course. I don't know what's going on here. It's set up. Yeah. Okay. Actually, that holding all else constant is sort of always understood. If I'm changing one variable, it's understood the others are being held constant. Otherwise, we have, it's hard to tell what's happening. So like even with this one, the yield will increase as the credit risk increases, holding everything else constant. Okay, so I guess that isn't absolutely necessary. But anyway, yield to maturity will increase as market rates of interest increase. If the Fed raises rates tomorrow, the yields of all the bonds in the economy will drift up to reflect that. Okay, so there's a tendency for rates to go up and down as a whole. In other words, there's a very strong correlation between them. So if the Fed raises rates, everything across the board goes up. The yields in all the bonds in the economy, mortgage rates, car loan rates, credit card rates, it all tends to go up and down. Not necessarily by the same amount, but they tend to go up and down together. So there's a very strong correlation between them. Anyway, so what we have here is in our chart is the cash flows. Now, the yield is what's determining these two columns. This PVCF stands for present value of the cash flows. Actually, let me see if I can find a home for this. So why does it keep doing that? I did something I shouldn't have. I know that. It's really aggravating, I tell you. Okay, PVCF is this is my abbreviation, present value of cash flows. So whatever this cash flow is, this is the present value. Now here it was calculated in a very simple way. Algebraically, well, let's take a look at it. So what I've done is I've taken that cash flow, B4 is the cash flow for this first year coupon, B4 divided by 1 plus the yield. Now, if you notice, I put the dollar signs there because that's something we don't want it to change. That's a locked in cell reference because I'm going to drag that down and I don't want that to change. But I do want the B4 to change because each row, the cash flow is this one. That should change. The exponent, same thing. I want that to change to reflect the year in which I received the cash flow. Okay, so you can see what I've done here is equivalent to doing this. It's going to be the cash flow. All right, I'll write this as CF because it could be a principal payment over 1 plus R to the T, where R is the yield to maturity. And then T is simply the time at which it is received. In other words, how many years in the future? And that's the present value of that cash flow. Okay, so that's really all there is to it. Tell you what, let me just to make some more space here. All right, here we go. I just want to clean this up a little. So all four of these are the same. Okay. And see, this is the genius of Excel. Once you got the formula, if you set it up correctly, you should never be necessary to type it a bunch of times. You know, it's there. You just drag it down now and it fills them all in. And if you notice, the yield continues to stay at C1, but the cash flow and the exponent will change to reflect what year we're in. Now, this last one, this is something that's unique to the Macaulay duration formula. All I've done here is I've multiplied each of these cash flows by the time at which they're received. Okay, so you saw that in the formula. You don't see this with any other formulas. This is something unique to Macaulay duration. So I'll add that down here. PVCF is the time weighted, we're going to call it, present value of the cash flow. Okay, so that's what that represents. That's the number that we need for the Macaulay formula. Now, I do want to point out here a couple things. Actually, let me do this. Let me go get the Macaulay formula. Here we go. So column C The way it's been set up here is that in column C, the first three cash present values, these three, represent this term. If you were to add those three up, you would get that first term. And then this number is this last term. Now that I'm looking at this formula, by the way, I just noticed something. I'll have to fix this. That 1 over P was supposed to be multiplied by the entire expression. So there really should have been some brackets here. Yeah, I'll have to update that later on, but just be aware that this entire set of cash flows, all of these are then ultimately divided by the price. Okay, so the way it's written here, that is actually not correct. The 1 over P applies to both of these terms. So anyway, this number and this number here, the sum of these present values is the price of the bond. Okay, now we already knew that, but here we've been able to confirm it. Okay, in other words, if these two were different, then that means we've made a mistake, right? The price of the bond, as we know, is the present value of these cash flows. And so you can see that they do in fact add up to 960. This is, like I said, this is something you don't see in other types of formulas. So the way this has been structured, the Macaulay duration is nothing but the ratio of these two terms. Okay, so in other words, all you've got here is T sum of these over the sum of these, or you can think of it as this, because it's the same thing. The sum of the present value of the cash flows is the price of the bond. So when you're done, you have 3.62 as your Macaulay duration. Now, this is where it gets a little iffy. The interpretation is a little awkward, let's just say. Basically, what they're getting at here is this, and I've seen it illustrated with this very unusual diagram. It's an attempt to capture the average time that it takes to receive all of your cash flows. And so in some of the textbooks, you'll see that it's illustrated by doing something like this. And, you know, I agree with you that that's a very difficult thing to think about, the average time until the cash flows are received. No, we don't, that's not very helpful. But you'll see in a minute why the modified duration is so straightforward. But what I've seen done in the textbooks is this. Look at the times until the cash flows are received. So in other words, we receive 70. What they're doing is using a series of bars. And you're supposed to imagine that Macaulay duration is like a fulcrum. Imagine this is a seesaw from, you know, elementary school, and the weights of the cash flows will only be in balance if the fulcrum is at 3.62 years. If I move it somewhere else, it'll tilt up or down. So this is the way it's meant to be interpreted. That's the point at which there's a balance. So in other words, it's on average 3.62 years to capture all your cash flows. Now, I agree that that's a very tricky thing to think about. So luckily, though, the modified duration came along and is much simpler to interpret, which is why we see it used all the time. The modified duration is, let me jump ahead a little bit. In a nutshell, I just skipped through the derivation. The modified duration is very closely related to Macaulay duration. In fact, let me show this to you first. The D by itself is modified duration, plain D. Is Surprisingly straightforward. If you took your Macaulay duration and divided it very simply by 1 plus the yield, the result would be your modified duration. So it's easy to calculate this in a spreadsheet. We're also going to see how to calculate it with calculus. So if you come back here, you'll see that the modified duration is DMAC, which this is what we're calling in the slides DMAC, over 1 plus the yield. Oh, 3.34. Now, this is a much easier number to interpret because if you look at this definition really quickly, what you're seeing here is that the modified duration is basically the slope of the price yield curve So if you drew a tangent line here, oh, what did I do? Hold on. This is supposed to be R. The slope of this tangent is, of course, negative. Sorry, it's just dP over dr. Right, of course. What else would it be? I mean, except, we're used to seeing X and Y, but I mean, it's the same idea. The only thing that's different, though, than what you might have expected is actually there's two things we have to do. There's two ways we modify this formula. Number one, we put a negative sign. Now, why is that being done? Well, because obviously the slope of this price yield curve is always negative. Now, the reality is negatives can be confusing. Okay, like for example, if you look at these two numbers, which one is larger? Well, of course, the -3 is larger, but it's hard to wrap our minds around negative numbers. So as a convention, we get rid of the sign when we calculate duration. And the way to do that is to multiply this by -1. Then we divide by the bond's price to make sure that all the durations are being calculated on an equal basis. In other words, the duration is designed. Let me add this in here somewhere. The modified duration can be thought of as the percentage change in a bond's price due to a given percentage change in the yield. Okay, so in other words, if you go back here and you see that modified duration we just discovered of, was it 3.34, means that if yields rise by 1%, bond's price will fall by approximately 3.34%, and vice versa, meaning that if the yields go down by 1%, the price should go up by approximately 3.34%. It's never going to be perfect, but it'll be a very good first approximation to the actual change of the bond's price. Now, the reason why this P needs to be here is because if it isn't, it'll appear that the bonds with higher face values will always be riskier than bonds with lower face values, even if they're not, because we're stripping out the effect of the price so that we're able to compare all the bonds in the economy on an equal footing. Okay, we'll see that more of that later on. If we leave out the P, we're going to end up with a measure called dollar duration, which is more difficult to interpret because it's not only counting or measuring the risk of the bond, but the price of the bond as well. So in other words, it gives you the impression that the higher face value bonds always are riskier than the lower face value bonds, which is of course not true. So the P, putting the P in there, strips out the effect of the bond's price so that what's left is just the sensitivity. Okay, so that's why that's there. And so what we end up with is called modified duration. This is the one you're going to see on Wall Street. Okay. Oh, you know, an insurance company might use a Macaulay duration for, you know, whatever they're doing there. But for as far as Wall Street is concerned, portfolio managers who are managing bonds, they're going to be looking at the modified duration numbers. But the advantage of this, now, if we didn't calculate, though, the Macaulay duration and then convert it with this very simple conversion, very simple, this is what you'd have to do instead. Oh my God. And that's because what you're doing is you're taking this pricing function and you have to differentiate it with respect to R. And you can see that can be quite a mess, especially you see this term here. This is the sum. In other words, we're going to need one of these sums for every single coupon payment. So this expression could get really long, like in a hurry. Now, by the way, one of our assignments will be to actually reproduce this formula in VBA. So we're going to be introduced at that time to the concept of the loop that'll help us run through a lot of different calculations. But you can see this is kind of messy. And so the ability to calculate Macaulay duration first in a simple spreadsheet and then do this conversion is very, very helpful. Okay, computationally that is. And often you see both of those numbers reported anyway. In fact, Excel has functions built into it that will do these. In other words, if you are not inclined to learn the math, you could actually do these with Excel's versions. Let me just show them to you very quickly. Let's see. So now here we have to watch it. Now there's one thing that drives me crazy with the financial, sometimes with the financial literature. The word duration, when it's used by itself, as far as I'm concerned, I mean, it could in principle be either Macaulay or modified. What I've discovered is that when you see the word duration by itself, most sources use the word duration to indicate Macaulay's duration. And then use the term modified duration, of course, to mean modified duration. So we're going to find out in a second if Excel follows this convention. They have two durations. One is called duration and one is called M duration. And so the thing is, again, either one, the unfortunate reality is modified and Macaulay both start with an M, and that's the source of a lot of confusion. So let's do this. Let's use Excel's versions of these functions. So we go to this insert function bar or tab. So you can see they've added something else in there. They have duration, M, and P. Yeah, let's not do that one. Oh, see, now they've added it. M duration, in the past, the instructions here did not make that clear. They're telling us right off the bat that M duration is Macaulay duration. Okay, that's good to know, because otherwise, now the only unfortunate thing is that their formulas require information that we don't have here. They need a settlement date, which is the date on which you officially take possession of the bond. We need a maturity date. And when they say date, they mean the exact date, like March 3rd, 2020 or something like that. So if you don't have that information, well, you're not going to be able to use Excel's formulas. So I think we'll just stick with our approach. But just be aware that these functions do exist. Okay. So anyway, so what I've done here though then is this, just as an example to show you how this works, is what I said was, listen, why don't we try this? If you change the yield by 0.01%, now, by the way, we need to review this very quickly. As far as interest rates are concerned, there's a measure that's frequently used on Wall Street called basis points. So let's learn this right now. Okay, so the way this works is that 1% equals 100 basis points, or they're often abbreviated BP. 0.1%, therefore, is 10 basis points, or we'll just simply abbreviate 10 BP. And 0.01% is 1 basis point. Now, you're probably wondering, why do we need this measure? What's the point? Well, because it eliminates any potential confusion. Let me just give you a quick example of this. Suppose that the yield to maturity of a bond is 5%. Suppose you are told that the yield has risen by 1%. Now, usually this is understood to mean that the new yield is 5 plus 1, which is 6%. But it could also mean that it went up by 1% of its current value, which would mean it went up to 5.05%. So that there's some potential for ambiguity here. If you use basis points, though, if the yield is 5% and it increases by 100 basis points, then it rises. There's no question in your mind that it goes to 6. If it rises by 5 basis points, then it rises to 5.05%. In other words, there's no doubt in your mind. Whereas if you say percent, that could get a little tricky. In fact, sometimes in the first case, sometimes we call this going up by 1 percentage point. But again, you can see the potential for ambiguity is there. So by using basis points, there's absolutely no question in anyone's mind what you mean. Okay. So that's why we frequently prefer to use basis points when we're talking about interest rates, especially when we're modeling, very advanced concepts like the measures in this chapter, and especially when we're talking about derivatives. We have to be so careful with our terminology with derivatives. So anyway, what I wanted to illustrate here is this. Let's just say that the yield is at 8.21 and it goes up by 1. This is 1 base. Oh, you know what I should have done? I just realized what I left out something that I intended to do. There we go. Now we have a complete set. Okay. 0001 like this means 0.01% or 1 basis point, which means that the yield is going from 8.21 to 8.22. So what I did here was this. The price is currently 960. If I change this, if I add 1%, well, actually, here's what I'm even going to do even better. The price changed by about 32 cents. It went down, of course, by approximately 32 cents. So I wrote that down here. So you can see the change in price as a result of an increase by approximately 1 basis point. The price went down by about 32 cents. Percentage-wise, That's about 33.41%. Now, with the percentage change, I've taken the absolute change, which is, if you notice here in the notation, it's listed as delta P. Okay, let me just put that over here. And then this percentage change in price would be this divided by the price. So if you notice, it's negative 0.03341. Well, the duration is 3.34. And so this is more or less exactly what we would have expected. Okay. So this is the change in the percentage change in the bonds price when the yield changes by 1%. So if I change it by 1/100th of a percent, then the price change should be 1/100th of this duration, modified duration. And that's more or less exactly what we see here. In fact, so in other words, it's almost perfect. Okay. Now, having said that, I do want to point out, though, I'll add it down here somewhere, and we'll get to this discussion later on too. But as the change in the yield increases, either positive or negative, by the way, the approximation to the actual price change worsens. So there's, if I actually change it by 1%, you'll notice that it's not going to be as accurate as it is here. So the duration is very accurate when the yield changes are small. As the yield change increases, it starts to break down a little bit. Now, let me show you why this would be happening. Basically, in a nutshell, the duration, the modified duration, that is, because it's the slope divided by a constant, therefore, it is a linear measure of non-linear of the sensitivity of a non-linear function. Okay, so in other words, if you go back and revisit the price yield curve, basically, here's your slope. And so when you're in this immediate area, if the yield changes by a trivial amount, like it goes from, let's say, here to here, the line and the curve are almost identical to each other. The line is the predicted change by duration. The curve is the actual change, because that is the price yield curve after all. So if I let the yield, let's say here's my initial yield, I'll call it R star. If it goes to here, R1, I'll call it, then you could see that the price will be pretty close. But if I move it way out here somewhere to R2, there's getting to be a pretty significant gap between that curve and that straight line. So in other words, if you notice that the duration is starting to understate the true value of the bond's price, and the same thing is true up here as well when the yield drops. So as we get further and further away from the initial yield, the predicted price of the bond is going to be understated, and by a progressively larger amount as R increases. So just keep in mind that the modified duration measure works well for small yield changes. After that, the approximation starts to worsen. Now, luckily, I mean, interest rates don't really change that dramatically over time, unless you're in a very high inflation environment or in a country where there's a lot of chaos going on. In the United States, if you look at the Treasury curve, it doesn't change that much, at least not over short periods of time. So this is less of a problem than it sounds like. But it does eventually start to break down. It's kind of like, you may recall, if you've ever had an economics class, this is the equivalent of calculating a marginal concept, like marginal cost. The marginal cost of a product means if I produce one more unit of that product, how much extra will it cost me? It works great for single unit change, but if you try to say, well, I'm going to increase my output by 100 units, then the marginal cost measure will be less accurate. And the same thing is happening here. So anyway, this is, now we know how both Macaulay and modified duration are calculated, and we understand how to interpret them, or at least we understand how to interpret modified duration. Don't worry about the Macaulay. I mean, it's important, but we're not going to need it in any of our derivatives pricing models. It doesn't show up again anywhere. It's really just important for historical reasons. And there's still some applications where it's helpful, but for our purposes, we're really focused on modified duration. Okay, so now what we haven't yet addressed is what can cause one bond to have, let's say, a modified duration of 3.34, and another bond for it to be, let's say, 2 or 7 or 16 or whatever. In other words, what factors influence the modified duration of a bond? Clearly, they're all going to be a little different. The question is, what causes one bond to have a different duration than another? Okay, so that's something we need to address. So yeah, here you can see the derivation. We're going to come back to this when we start writing code. Oh, by the way, yeah, there's this discussion. We'll get to this in a second. I just want to mention um, what factors influence a bond's, or I shouldn't say influence, determine a bond's modified duration. Yeah, because this is one of the interesting things about the bond. I think I mentioned this before. The bond markets are sometimes called the fixed income markets because the cash flows are pretty predictable compared to, let's say, stocks. And the fixed income markets are heavily mathematical because of the predictability of those cash flows. And so everything is very precise in the bond markets. Like if I change one factor by a certain amount, I can be pretty confident it'll have this other impact on the bond's price. So what really determines the bond's modified duration? Number one, longer the maturity of a bond, greater will be its modified duration. Okay. And then number two, now this one is not, I mean, that one is pretty straightforward. I mean, it should be pretty clear that if there's more cash flows, then there will have to be a larger duration because there's more terms. It's really that straightforward. But this one is not very self-explanatory. We'll get to this though. The higher the coupon rate of a bond, the lower will be its modified duration. And now that's a very strange result, but we will discuss this fairly soon. I just want to mention it right now that these are the two main determinants of a bond's modified duration. Also, in general, when interest rates in the economy, when yields are higher, the modified durations of bonds tend to fall. Okay. But and again, we'll discuss these as we go along. Now, convex. Now, remember from calculus, the two ideas that we're about to discuss, we have this notion of concavity and convexity. And this has to do with the rate of change of the curve, the slope, that is, I should say, the tangent curve, the tangent line to that function. So you'll remember there are four basic cases. So we'll just do this in general for X and Y. So here, if you notice, the slope is increasing, but at a decreasing rate. So the first derivative is positive, the second derivative is negative. Okay. Now, oh boy. I'm not sure if I have enough room for this. All right, I'm going to try to see if I can squeeze in all four cases here. Nope, that's not what I want. I'd like to keep the positives. Here we go. Together. Oops. So this time the slope is not only positive, but it's actually increasing in steepness as we move to the right. So the second derivative is positive. And then we have down here. So the slope is negative, but it's getting less negative as X increases. And then down here, they're both negative. So these two are convex, and these two are concave. So now you recognize the one in the bottom left-hand corner is the one that looks just like our price yield curve. So what we're going to do is introduce another measure of risk to go along with duration. It'll be, think of it as duration's companion. We're going to think in terms of not only the duration of a bond, but the convexity, meaning the curvature of this price yield curve. As now, for some cases, the way it works is that everybody looks at the modified durations for every bond. It's really important. It turns out that the convexity measure is a helpful supplement, let's say, but in many cases, the convexity measure is a very, very small number, and it makes very little difference. There's certain cases though where the convexity can make a huge difference as to the risk of a bond. So it's not as important then as modified duration. We still need to understand how it works, okay? Because it can make for some cases a big difference in the behavior of a bond. Now, what I have here is a very formal discussion about convexity. And when that's done, and by the way, what's interesting here is that we're going to get some more calculus in a bit, because it turns out that what we're actually doing here with modified duration and convexity is using our old friend from calculus, the Taylor series. Okay. Oh, yes. Remember the Taylor series of expansions. Remember there were Taylor series and there was Maclaurin series. We're going to review that, I guess, in our next session. And we're going to see how it ties together with duration and convexity, because that's really all they are. What they are is a Taylor series expansion to the price yield curve at a given point, where we're really only focused on the first couple of terms. The rest we don't really need. They're not really that important. But anyway, so I'll tell you what, since this convexity discussion is fairly involved, and it can be done in a couple of different ways. I think this might be a good stopping point for today. And then tomorrow or the next day, we'll pick it up. And right here, where we get more deeply into this concept of convexity. And then when this chapter is done, we're going to take a sort of a detour into VBA and introduce the language. And then we'll start looking at how the coding works. We'll start using some of these examples and seeing how we can reproduce these in VBA. Now, the good thing about VBA is anything that you can do in Excel, you can do in VBA. You're basically just taking Excel and adding more functionality to it. So all the work we did in Excel can be directly translated into VBA. Anyway, so that's something to look forward to. I guess we'll stop right here. And then the next time we meet, whether it's tomorrow or God, I'm completely thrown off by the holiday. The next time we meet, we will discuss convexity in very great detail. Okay. All right. So I'll see you all next time. Okay. Bye.